I'm Lucas, and I'm going to talk about the volumetric fog that we did for Enshrouded. A little overview about the talk I want to give to you. Give a quick intro about myself, about our company, and the game. Little overview of the problem that we are trying to solve, or that we need to solve for our game. I'm going to show you some pictures about the prototypes we did. And we're doing the production. We tried fog rendering 2 times. I'm going to show you the first try that we did, which ultimately failed, and the second try that we are shipping right now. And I'm going to end with a little conclusion. Who am I? I'm Lucas Feller. I joined Keen Games in 2018. I started as a gameplay programmer, but because of prior experience in my theses and also personal interests, I started becoming a graphics programmer with the start of Enshrouded. I'm working at Keen Games. Keen Games is an independent game studio located in Frankfurt. We have around 70 people, and we have a very hybrid working structure. So some colleagues are working solely from the office, some are part-time in the office, but the majority of colleagues are actually working fully remote. Our previous project was Portal Knights. Maybe you heard about that. And the current project that's in early access since January this year is Enshrouded. Enshrouded is a genre mix of action RPG and survival game. It has a completely modifiable voxel world, so the whole world, the whole terrain you're seeing, and all the buildings are completely voxel based and can be changed by the player. Fog is a core element of our game, so I'll show you some pictures later and then you'll see. Our technology is completely custom. We call it Holistic Engine. It's a custom game engine written from scratch. It has a very long history already. It has been used in all previous projects at Portal Knights, but it is under continuous development, and we're always keeping up with recent developments and fitting it to whatever game projects are coming up. Currently, we are shipping Enshrouded on PC using the Vulkan API. We have an internal Linux build, and console versions are in the works. I'm going to show a quick video about Enshrouded. Just some impressions. You can see there's fog everywhere in the game. You can deep dive into it. We have a dynamic time of day system. And also in the night, we have a very mysterious atmosphere. This is one core element of our game. We have those fog plants, and when your goal is to destroy them to clear the area of fog, to clear the area around the plant of the fog. So that was a quick overview about how our game looks like, and I want to talk a bit about how we achieve that. So the basic problem that we want to solve is the basics of volumetric rendering. So in general, we have particles in the air. They have 4 different properties, what they're doing with light. They either absorb light that travels towards the observer. They can emit light in the direction of the observer. They can scatter away light that comes from behind towards the observer, but then is scattered away. Or light that comes from anywhere else is scattered towards the observer. You would typically solve that by ray marching, so you take a ray from the observer in small steps, and at each step compute how much light is scattered or emitted towards the observer and how much light from behind is absorbed. So the stuff that we want to render for our game is shown in this little overview. It's an actual piece of paper from production that laid around on my desk for a year, so that that I'm always reminded about what we're supposed to render. So we have clouds in the sky, we have an atmosphere everywhere, we have exponential height fog, we have those foggy areas down below. We have like those little, I call them game modifications. That's those pieces of the world that get cleared of fog when you destroy those fog plants. And the player or enemies, for example, can throw fog grenades to spawn like little fog phenomenons, just as a nice gameplay effect. We started out with prototypes because our studio did not have any prior experience with volumetric rendering. For that, we built on the renderer of Portal Knights, our previous project, and just hacked it and added some volumetric rendering, just so that we can get some initial experience as a team, like both programmers and artists, about what volumetric rendering is about, what we can do with it, and what the challenges are. And we based that basically on Frostbite's approach with the voxel volumes. Later prototypes, now in the new holistic engine, where we were just rasterizing a plane for the area where we want to have fog and did a little ray marching in the fragment shader. And later that moved to a full screen compute pass. Now to our first approach to render the fog. Just as a reminder what we want to render, there's the image again. And we kind of separated that into two coarse things that we want to render. The first one we call analytic fog. That is like participating media properties that arise from various models. For example, the cloud models, the height fog, ground fog, and the game modifications. Those are participating media properties we compute somehow in the shader based on data. And VFX injection is triggered by our VFX system. That's where the artist can spawn like spheres or cubes modulated with 3D textures and noise and distortion and whatever to dynamically add fog on top of that. And also remove fog, very important. As a first try to model those big fog areas that we have in the game, we went with a height map, because the initial idea was that we have a pretty strict separation between above and below. So we just took a world space height map with height in one channel, and in the second channel we added like holes, what we call them, to be able to model like very sharp holes in this height map without requiring too many pixels. And we also used this height map to approximate volumetric shadows. So, for example, for any point in the world, we would take a ray towards our primary light source, intersect with some medium height, sample the height map there a second time, and then kind of approximate what the height map in between might look like. It's of course a very coarse approximation, but yielded some nice results. But at some point we abandoned this height map only approach because it didn't really match anymore, because we wanted to do more with the fog. So we went with a full 3D voxel grid to modulate the fog. That gave us way more flexibility for level designers. And we already had very sophisticated voxel modeling tools, because we built all of that already to model our voxel world, the terrain. And we kind of just added a second output that would then also write fog voxels. And another nice property of a voxel grid is obviously a hierarchical representation, but more on that later. To render this fog, we also used the approach, or we were inspired by the approaches used in Frostbite and Red Dead Redemption 2. So for the near field, we have 3D textures that are mapped into the frustum, into the view frustum. And for the far field, we switch over to ray marching. Now, at this part in the project, we were still using MSAA, and no TAA at all. So we tried to get all of this working with those restrictions. For rendering shadows, it's very straightforward, also inspired by the other mentioned works. We are using 3D volumes in a cascaded fashion and align their z-axis to the direction of the primary light source. So in a first pass, we would just initialize them with participating media properties, and in a second pass, integrate from the light source down, from top, which is near the light source, and then away from it. And that gives us information about how much shadowing there is from the fog for any position inside those cascades. As I said, we were still rendering with MSAA, and that has proven to be quite difficult to handle for the ray marching part. We tried ray marching for each MSAA sample, which was way too many samples, way too slow. So we also went with doing one ray marching, one ray for each 2x2 pixel grid, which on the other hand meant, with 4 times MSAA, that we would have to write out up to 16 different depth samples. And we have to account for those, because if we would just take any sample, a medium, an average one, or just the first or just the last, that we would basically erase all of the nice anti-aliasing that we got from multi-sampling, resulting in this, in horrible artifacts like those. So what we did as an approach was, in a single compute shader, read all 16 depth samples that we have to account for, sort them with a fixed sorting network, and while ray marching along the way, if we would step across a depth sample, write out that one, and then continue ray marching. And that way we have a nice output for every single depth sample and beautiful image. But unfortunately, it already sounds pretty slow. I mean, it was faster than expected, but still too slow. And at some point, we hit a dead end and didn't continue with this approach. So second try was basically Red Dead Redemption 2 again, but now with much better understanding based on the experience we gained with the first fog renderer. And we finally tried to use TAA, because we saw that with just MSAA and no TAA in the fog, there's not really a good possibility to get all of that running, at least for the data that we want to render. So let's get a bit more into detail how all of that works. The general stuff that we want to render didn't change, so this is just a reminder again about what we are looking at. So going from far away to closer to the camera, the first thing we want to render is the atmosphere. We inspired from Frostbite, we based our atmosphere models on previous works. I'm sorry, I can't pronounce the name, so I don't even try. But I have full references later on a slide later. We basically implemented those models. They compute, they result in lookup textures that we can use, and that way, sampling the atmosphere becomes very cheap. What we found out what is very important for the atmosphere is that the transmittance value is specular. We will see later, and in a lot of stages in the fog renderer, the transmittance value is simplified to a scalar value, but that affects the look of the atmosphere a lot. So we have to do that specular, and that's why we are sampling the atmosphere always very late in the fog renderer. But that is fine, because doing a single sample into a 3D or 2D lookup texture is super cheap. For the clouds, I also don't have really anything to add, rather than refer to the excellent talks by Andrew Snyder. He did great works on how to model clouds, explained that very well. And we basically took a lot of inspiration from that. We are leaving out some details because we didn't didn't have the need to build such a sophisticated model yet, but yeah, we were happy with the basics for now. Now about the fog voxel grid, as I said, our fog is represented in a big voxel grid that spans the entire world. We have a resolution of 1 meter per voxel, and we are storing the fog as a R8 UINT 3D texture. And in each voxel, we store an index into a lookup texture, and that lookup texture contains the participating media properties. We are doing that because that way, like with just 8 bits per voxel, it's significantly smaller than anything larger. And we are supporting some changes to the volumetric fog grid. For example, based on player progression, you are unlocking more parts of the world, which we are visualizing by using the different media properties for the fog. And also, as you saw earlier in the video, you can destroy one of those fog plants to clear areas of the world, which basically means that fog density in that area goes to 0. And we can represent that, or like we can update the voxel grid by just updating the respective index in the lookup texture. So each separate instance of an effect that we want to render, or each separate instance where we want to have different participating media properties, gets its own index in the lookup texture. And when any of those changes, we just have to update the lookup texture. So the big fog grid, the big 3D texture, can stay completely static. So we are just loading that from disk and never touch it again in the runtime. We are computing a hierarchical bit mask on this 3D grid for efficient empty space skipping. I'll show you that very soon. And yeah, also, like we never have the whole voxel grid in memory. Like we have the full resolution in memory only around the camera, and further away we just rely on the hierarchical bit mask. This bit mask looks like this. So each, like the third dimension is not visible in this image, but for each 4 by 4 by 4 block of voxels, we store 1 bit per voxel about whether it's filled with any value or not. This is exactly 64 bits, so 1 UINT 64, which we can efficiently load on the GPU. That's the first hierarchy, and the second hierarchy, you can exactly see one level of that, is again a 4 by 4 by 4 block of those UINT 64 masks. In that way, with few steps, we have a very nice hierarchy that we can efficiently step through. I'll go into a little bit more detail about that later. For a lot of fog effects that we render, we rely on SDFs that we have. We have SDF representations of the voxel grid, which we are using to add like a little bit of a thicker border at fog transitions, just so that it's more clear about when you're entering or leaving the fog. We have an SDF of the whole world, which we are sampling to add a little bit of ground fog near the floor. And zones where players can build stuff also have an SDF representation. It's just a simple boxes. We are using that to remove ground fog again in areas where players can build, because we don't want their builds to be, we don't want ground fogs in their builds because that doesn't look very nice. For VFX injection, we have a very simple API with a lot of properties that the VFX artists can use. So you can see it's just positions, size, some 3D image, UV offset and scale, and participating media properties, and a sort key. And from VSX, we just write out these instances into one big storage buffer. And in a second pass, based on the sort key, we sort them. That is important because you can add and remove fog. And this is order dependent, so VFX need to have some control about in which order this happens. Yeah, and for example, you can see here a lot of the VFX artists add a little bit of detail for the fog planes, for example. So this is all done with this VFX injection. To sample this VFX injection, I just have this little code block. Like other works are doing that in separate compute passes or something. We managed to get it fast enough using wave intrinsics. So for one wave, we are computing the bounding box of this whole thing. And then then each wave reads one fog instances and reads one fog instance and does coarse culling about whether it's visible or not. And then in a scalar fashion, we go over all the non-culled fog instances and do the actual fog injection computation. And that became very fast. And like if someone is very interested in that stuff, on this slide there's a little bug. Maybe you can find it. Yeah, that's about the fog render, about the fog stuff that how we are representing that in the world. And now about how we render that stuff. So we split our rendering basically in 3 layers. Like other existing work did that with 2 layers, so one far layer and one near field. But we split it up in 3 because that made things a little bit easier. We have separate rendering algorithms and temporal filtering passes for each of those. And they're just composited on top of each other because they have a very strict ordering. On top of the final scene caller. So that's what it looks like. We start with this. This is the lit scene, but without any fog yet. And now back to front, we add the sky and clouds layer, the far field ray marching layer, and the near field voxel layer. Clouds rendering, again, largely inspired by Andrew Snyder talk, but also with a way less sophisticated shading model. We are rendering that into a full-res E5 BGR9 format for the luminance and into a R16 texture for the transmittance. It's done in 2 passes. The first pass is simple ray marching with dithered, blue noise dithered ray offset. And in a second pass, we filter this result, either temporal if possible with the previous frame, or for pixels that don't have valid history yet, we just do spatial filtering, which means Gaussian blur with the neighbors. That's what it looks like. So the ray march output is very noisy, very pixelated, but once we add temporal filtering, it becomes super smooth. Clouds rendering, we are only doing that on sky pixels, so only where the depth buffer is exactly 0. And the start of the ray marching is the intersection of the viewing ray with the sky dome. And it basically goes towards infinity. But we only have to ray march the cloud layer because for the last ray, for the last part of the ray that goes towards infinity, towards outer space, we can just have a look up into the lookup texture of the atmosphere model. The far field rendering, that is ray marching from the end of the near field towards the sky dome. We have a half-res E5 BGR9 format texture for the luminance, and again R16 for the transmittance. But that is then upscaled to full resolution and temporally filtered. For the far field ray marching, we found that sampling our fog models and shading was still too expensive. So we optimized that by introducing an additional pass that would first find out where along the array interesting segments are happening. So that gives us the possibility then to sample those ray segments where not a lot of interesting stuff is happening, so basically where only the atmosphere is. We can handle those separately to the expensive ray segments where thick fog is there, where we have to compute complex shadows and shading and everything. And we find those segments by first doing a pass where we intersect the fog voxel grid using an extended version of the fast voxel traversal algorithm. And that would basically give us a 2D texture where for each ray we know when we are we will get 2 points, an in point into interesting fog data and an out point. And we are accelerating that using the hierarchical bit mask that I introduced earlier. So for a view ray, we start at the camera position, and then we first read out the highest level of our hierarchical fog grid. And in this case, it's not empty, so there's stuff inside, so we have to go down one layer. But then we can check like each of those, the initial 3 grid cells of the next hierarchy level are empty, so we can just skip over those. And only the last 2 levels we have to go through separately to find the intersection. And yeah, using the bit mask and a variation of this algorithm, we can step like large portions of the rays very easily. So we don't need a lot of samples to find the interesting intersections. As of recently, our game supports dynamic weather. So we are using the same technique to walk through the weather map and find where weather phenomena that affect the fog renderer where they are along the view ray. With those intersection maps, we get up to 3 ray segments, either also in this order, atmosphere only and full fog, and maybe atmosphere only again. Like any view ray can have 1, 2, 3 of those ray segments, and no, 0 to 3 of these ray segments. Like if the depth buffer is closer to the end of the near field, you don't need any ray marching because that segment is completely handled by the near field. And then for the atmosphere, we do a fixed amount of 4 samples. And for the full fog portions, we do a fixed amount of 16 samples. And then again, atmosphere only, which is 4 samples. So we have a fixed amount of samples, which also means that the step width of those samples is also fixed for each ray. And that gives us completely deterministic performance. We tried adaptive ray marching first, but we didn't manage to get a good solution with that, or a solution that was cheap enough. So that's why we went with fixed samples, and that works surprisingly well. So that's how the output of this far-field ray marching looks like. We are doing that on a min-max downsampled depth buffer, and also apply dithering offsets. That gives us this very noisy output. We are upscaling that using the dithered upscaling, which is also inspired by Red Dead Redemption 2. So for each target output pixels, we would just take 4 random samples in the neighborhood, do depth rejection on those, and average them together as long as they roughly apply to our target. And this gives us this noisy full res image. And this image is then temporally filtered and gives us a smooth result. Now to the near field. That is also inspired a lot by the frostbite approach, but we have an additional view volume, and that is the scattered light volume. The scattered light volume just stores light, light that is isotrophically scattered at a point in space without any participating media properties yet. We introduced that one because we also wanted to shade our VFX particles the same way with the fog, so that the two blend in together very well. And we need the very same result for the fog renderer as well, so we are just storing that result first, and then we use it for the 2 parts of the pipeline. Then for participating media properties, we have 2 times 16-bit float RGBA textures. From that, we compute a source term texture, and as a final step, we integrate the source term texture, which again yields us a luminance texture and a transmittance value. And yeah, both the scattered light and the source term volume are temporally filtered. The others are not. So just some example images. That's what the scattered light volume looks like. For the participating media volume, again, we are storing the scattering, absorption, and emissive value. And yeah, as I said earlier, we are initializing this whole volume in a single pass, and we are done already. Other works do a second pass, but we managed with just a single one. We get the source term volume by using the participating media volume and folding that with the scattered light volume, and we add the atmosphere model folded with the directional light visibility on top of that. Yeah, and then we integrate that as a 2D pass from the camera position away, and this yields this 3D voxel volume, where for each point in the space we know how much light is emitted towards the observer and visible at the observer, and how much light behind it is absorbed. So those two values are called luminance and transmittance. And in this little debug view, you can see how that looks like in the game. We had one issue with our fog render, because again, it was too slow to sample our fog and apply the shading with a very nice resolution. So other works we found have a resolution of like 4 pixels per voxel volume, but we didn't manage to get acceptable performance with that, also because we have a very low target hardware. We want to run like sufficiently fast on the Steam Deck and also still on the GTX 1070. And we managed to get acceptable results by faking like higher resolution, by applying noise, by doing integration through the source term volume. We are applying a offset that's modulated with the wind, and a noise texture along the ray. I can show you some image. I hope that's a bit more clear then. So that's what just going straight along the ray looks like. But if while traveling along the ray, you're offsetting the sample positions by noise that's modulated with wind, we get those nice little swirls. And that's what we are shipping in the game right now. It's also looks very nice in movement. Maybe you can see that it's pretty subtle, but in the game it adds a lot. What we are losing with this approach, obviously, is like very hard shadow edges. Yeah, because it's a very final step, we are kind of modulating everything again, but it fits our game nicely, so we are shipping with that. And that way we can get away with a very low resolution for all the voxel volumes. Like we are at 16 pixels per voxel for all the other volumes, except for the final view volume. For shadows, there's not much to add. It's still 3D, cascaded 3D shadow volumes. And again, we're initializing that one in one 3D dispatch, and then do a 2D dispatch for each cascade in the direction of the light. It's like we have one 3D dispatch for each cascade, and each cascade, like we go from outer cascade to inner cascade, and each cascade, like as an initial shadow value, reads the upper cascade. So we can, in the end, we can just sample the one cascade, and with one sample we get the full shadow volume. And the outer cascade is initialized with approximate volumetric shadows for clouds. yeah, it's basically the same image as before. We can see those small cascades, and we would compute them outer cascade first. Then for the inner cascade on the top layer, we just sample the outer cascade to get some initial values. Yeah, my conclusion, everything you just saw and everything I just explained is still work in progress. Like, we are still in early access, so yeah, we still have many ideas what we want to improve or try out. Also, a lot of the performance characteristics changed along the project due to optimizations that we did. So some of the shortcuts we took to improve performance may have to be revisited or can be revisited, and we can improve quality again. Issues that we have right now is that due to this very strict separation in those three rendering layers, we can't move the camera into the clouds. That's where everything breaks down. The overall quality is still lacking in our mind, or in our opinion, so we want to improve on that. And also our temporal filtering, which is also that the team does not have a lot of prior experience with, also has some issues, but yeah, we can still improve on that during early access. Another challenge during development of this fog rendering was that the engine changed a lot during development. Like, during production, we decided to move away from MSAA and use deferred rendering instead. And also the infrastructure, how we are loading shaders, changed. And yeah, those two kind of developed alongside each other, but also inspired each other. Like, problems that we had while implementing the fog renderer, which is with its multiple passes and render targets and whatnot, inspired some designs, for example, for GPC, to make all of that stuff more easily to work with. Yeah, another thing that we found out, like that working with that much TAA for the first time as a team, is that you have to be very careful with stacking different temporal filtering techniques on top of each other, because it's very easy to mess up one of the earlier temporal filters, but you don't ever see those issues because later temporal filters will hide those issues. That is a bit problematic because in the end you might have an unexpected result, but it's not really clear where it comes from because it kind of sneaks through the whole pipeline then. Yeah, some words of courage that I want to tell you is that this, like, for us, fog rendering and that much TAA was a firstie for us. We are implementing those things while the game is in production, and sometimes it can be very hard. Like, we had failed approaches, we scrapped our first fog renderer completely, but that is not really a failure or wasted time, because this process gave us a lot of experience, and for everyone in the team. So yeah, don't take those things as a failure and as a bad thing, but every failure is an experience that you gained. Every success as well, of course. But this can only work if you have a very supportive environment and team. Like, sure, if you're working in a company, your team has to be supportive and support you to try out new things and, if necessary, fail doing those things. If you're not working in a company and in your free time or whatever, the same applies to your environment, like your friends or family or whatever. And also, like I said, we kind of based our fog renderers 2 times on Red Dead Redemption 2, but the first time we didn't have enough experience yet to understand many of those very important details that were expressed in the respective talks. So yeah, it's also fine to work, like get inspired by something, try to implement that, for whatever reason fail, and then the second time you'll understand way more of that because a lot of the other basic issues now click to you. Yeah, all of that wouldn't have been possible with a lot of those great, prior work. I listed all of that here. Probably I'm missing some because there's a lot of great work already out there in the graphics community that is very inspiring. Yeah, our company is actually looking for a junior graphics programmer right now. If you found that mildly interesting and understood some of that, that's a perfect precondition. So if you're interested, you can apply. And with that, I want to thank you.